My name is Richard O. Calkins. I'm glad to be here this morning, and I'm going to be talking about the mediums of light, which are hiding in plain sight. We couldn't see them because we weren't aware of what it was we should look for, but they're described in Maxwell's equations. Oops, that one doesn't do it. Which?
The bottom button.
That's the one that does it. There we go. Okay. We couldn't see them because part of the human condition. You know how the Indian tradition has the wily coyote, who's the one who's always causing trouble? Well, the wily coyote is just the human condition at work. And being human, we had a lot of implicit assumptions about what mediums of propagation for waves had to be, and we hadn't really thought about them, but they have to be something physical through which the wave passes, and they have to be there whether the wave is not there, so the present, whether the wave is passing through it or not. But it is a stationary reference that the wave passes through. And the speed at which it passes is governed by the behavior of the physical medium through which it propagates, because the wave doesn't really actually exist. It's like a pressure in air. The pressure doesn't exist, the air molecules exist, they're just closer together. But that causes a disturbance, and because the air doesn't like to be squeezed closer together, it passes that disturbance on. Just like the political process, so if you're disturbed and don't know what to do about it, you pass it on. So much about that. Okay, I got to get going in, there we go. Now, as is common with implicit assumptions, it turns out that 80% of them are wrong. The first four don't apply because it's a totally different kind of wave. And so what we're going to do is, let's see, I'm going to cut down because I was going to go through, I'm going to go down to 14. Where's 14? I reordered this because what we're going to do is we're going to first look at air transporting sound, and then we'll come back and look at electric mediums. So I'm hunting for, okay, this is what I'm looking for. We're going to take a look at what the formula for the speed of sound tells us about the propagation of sound waves in air. And I'm using V sub s as the velocity of sound or speed of sound. And the equation is that it's equal to the square root of the bulk modulus of air divided by its density. But what the heck does that mean? That's what I call a what equation. It's not really an answer, it just says what happens. It gives you no information about why it happens, what's going on, but they stop there. So the question you want to raise is, okay, if that is, and the bulk modulus is just how hard is it to compress? How much pressure does it take to reduce the volume by a certain amount? Or how much do you have to reduce the pressure to let it increase by a certain amount in relation to what's already there? It's a lot harder to press a cubic foot out of a 2 cubic foot thing than it is out of a 20 cubic foot thing. So that's basically what the bulk modulus is how hard is it to compress, or how hard do you have to hold it to keep it from decompressing. And of course the density is the density. So the $64 million question though isn't what Vs is equal to, it's what the ratio of the bulk modulus to the density is. And it's equal to the velocity of sound squared. Why is it the velocity squared? Why isn't it just the velocity? What's going on here that makes this thing that makes the speed of sound the square of the velocity? Well, we can fall into another implicit assumption of old quiet and say that means that it's the velocity of air multiplied by the velocity of air. But if you step back from that implicit assumption, you can say, well, actually, any two velocities whose product is equal to the value of the bulk modulus over the density of air satisfies that requirement and would make the speed of sound, which is equal to that, equal to the square root of two velocities working in some way together. What might those velocities be that equal to the bulk modulus? Well, let's take the fact that we have a pressurized domain in air, which is the sound wave, and a less pressurized domain of air around it, which is the ambient air. Both of those like to expand, they don't like to be compressed. So let's take the ball of air that's the sound wave, the high pressure air, and go out and release it where it isn't constrained in empty space or in a vacuum. How quickly will it expand? Well, it'll expand, the rate at which it will expand is based on how hard the molecules of air are pushing away from each other to relieve the pressure. And then that is how quickly it'll move to expand, and we'll call that speed, its velocity when unopposed, because it's in a vacuum. Okay, so that velocity when it's unopposed is the distance it can move divided by time, how quickly it moves. We're going to do something different. We're going to take the reciprocal of that and say, how long does it take to move a certain distance? And we're going to use a little omega unopposed for the reciprocal of the speed at which it's moving, and I'm doing that because later we're going to compare it with the velocity of light, and we have to think in reciprocal simply because of the way Coulomb discovered and Maxwell discovered the behavior of light. Now the other volume, the other velocity is the pressurized wave is now not in a vacuum, it's in ambient air. And the ambient air is just like it, except it's at a lower pressure. So it would like to expand, but it can't because it's got an overwhelming pressure in the air, which then moves in, pressurizes this, which then continues it on. So you've got essentially two opposing forces, one of which happens to be stronger than the other and is therefore dominant. But those two, and we'll take the reciprocal of that one and we'll call that omega of being opposed. And it's 1 over how hard that would push if it didn't have the pressurized air in the way, how hard it's trying. So now we know what the two velocities are. They have to do with the two domains of air trying to expand and how fast they could innately do it if they didn't have something stopping, and what happens when the two of them are facing each other in the same place. So we've got two velocities that are equal to the bulk modulus over the radius in their square root. The square root of the two velocities, the product of the two velocities is what produces that, And if you then take the reciprocals, you've got that. If you take the one out, you've got that. Does that start to look familiar? Relative to the formula for the speed of light. So now we'll go back, if I can get back to where I was. Now we'll take a look at the speed of light. And we'll start first with Maxwell's equations, and probably most of you are at least as familiar, if not more so than I, but I'll go through it as I put it. Maxwell's first equation. This means the amount of electric field or electric charge that is coming from a location where you're measuring it, for example, a point in space, is equal to the density of the electric charge divided by some constant, it's really what's called a proportionality constant, because it turns out it's not equal to the density, it's equal to the density adjusted by an empirically derived constant from Coulomb's experiments. And we'll come back later to what is epsilon O. But some things we know about that is it's a point charge, that's what this is telling us. And as we move out from the point, the energy or the electric charge will be diminished if it's over a larger area. And something it doesn't tell us, but that we've also learned, is that like charges repel each other, and unlike charges, whether they're negative or positive, they repel each other, and unlike charges attract each other. And this is sort of like two domains of air trying to repel each other when you have like forces. Another thing we find, though, is that if you have a point charge and you go out a distance, we'll call it a distance r from the point charge, the reason, and of course it's trying to get away from itself because, in fact, this is a light field. You don't have to have two separate sources of a light field. If this is a positive charge, this is a light field too, and it also doesn't like itself. It's just like if you go to the center of the pressurized air, it's trying to move away from itself. And so that velocity when unopposed is if this thing doesn't, if the fields are stationary, then it can expand or dissipate the density of the electric field at the fastest pace possible. When you get out of R, it's spread over the interior of a three-dimensional sphere. And so the point of measurement will have a lot less, and the amount you should have less ought to be what you started with divided by the area of the sphere ought to be what you measured at point R. So if you have that much at the beginning, you have that much out of point R, because diminishing it as it spreads over the area of a sphere. But the thing we find is it isn't equal to that. It's proportional to it, but it isn't equal to it. So what's going on that makes it not equal to it? Well, the answer lies with Coulomb's equations. Coulomb found that it's equal to 1 over 4 pi, here's that little constant, times the amount of charge at the source divided by R squared. Why it's in that form, I don't know, because it makes more sense to me if I put the R squared over here and the epsilon over there. And now you can see this is what you should expect. And you have to modify it with this. And Coulomb figured that out, and he calculated very carefully and accurately what its value is. And since air or light moves through space, he figured, well, this must be something like the permittivity of space. It must be a characteristic of space that is causing it to be something different from just it's spread over a certain area. But if we look then at this, we find that's the same thing as the density of the electric charge in Maxwell's first equation. So we'll take that, we'll plug it in for there, and we'll rearrange it back to the order that Coulomb had on the bottom, and we find that this is just Coulomb's law, another way to state it. Except that Maxwell states that it's coming from, and whereas Coulomb just says it's equal to. There's an insight Maxwell had, Coulomb didn't, because coming from means motion, means dynamic. Okay, it's a little bit different from Coulomb's perception of that. So what you then have is the density at a distance. If we take the reciprocal of the velocity of expansion when unopposed, we get epsilon sub 0. In other words, it's going to push as far as the fastest it can when there's nothing to prevent it, because the field is stationary. Then the reciprocal of that is E sub O, or epsilon sub 0, so it should be no surprise son of a gun, that proportionality constant has something to say about the speed of light. It's not an accident, it's caused by the natural force with which an electric field repels itself. So that's all that epsilon is the reciprocal of the rate at which the field moves out from itself because of its innate repression. Oops, wrong. Now, so that's what we know from the first equations. Go to the second equation, we can get rid of it real quick. It says the amount of magnetic field coming from a point is 0. Well, it doesn't mean there's no such thing as a magnetic field. What it says is it's not a point field. You find a magnetic field, you find a looped field which has no beginning or end, it exists in an area, it doesn't have a point. So it's a different kind of field from an electric field. An electric field is a point field from a charged particle. A magnetic field only exists as a circular field. So we're done with that. We go to the third equation, it gives us something more interesting. It goes back to talk about electric fields. Sorry about that. And what it tells us about an electric field is that there's another source of an electric field, and it's a different kind of electric field than the point source electric field. This symbolism means that the curl of an electric field is equal to minus the rate of change of a magnetic field in time. Now, the minus doesn't mean that when that gets bigger, that gets smaller, or the minus just means that the field happens to curl in an opposite direction for an electric field than it does for the magnetic field that's creating it. So the faster that moves, the tighter this field is curled, and that means it quite literally. If the curl of the field is less, then it's a less dense field. The more you curl the field, the more field lines fit into an area, and the denser the field is. So what this is saying that the faster that moves, the denser the field is that it creates. And the slower it moves, the less dense. Now we go to the fourth equation, and it tells us something similar about the magnetic field that the third equation told us about the electric field. Except that we have here two sources for the curl of the magnetic field. One looks just like the one we saw in the previous equation, only it's the rate of change in the electric field, and it's multiplied by both of those pesky constants. So the rate of change in the electric field will curl a magnetic field, but also the electric field moving through a wire is the electric field in motion, and it will also create and curl a magnetic field. If the current is a stable level of current, that'll be a stable curved field, and in this case it's a field that is increasing and decreasing in its density. So the magnetic field at distance r diminishes 1 over 4 pi r squared, as we would expect it to, except again it's proportional. And we now know that what makes it proportional is it depends not only on what's there, but how quickly it can be delivered. It's got to push against something in order to have an effect. It's like a classroom full of students don't learn anything from the teacher unless she teaches. You know, and then that's an active thing, which is expressed in how hard it's pushing against itself. And so we've got to add that. And its reciprocal is 1 over mu. And so we then get to knowing that both of those are reciprocals of the velocity that an unopposed electric force can move to relieve itself, and that an unopposed magnetic force can move. And unopposed means the field itself is not moving. But if the field is moving, it has to create the opposite field. It has to curl it. If the electric field is moving, it has to curl the magnetic field. And because it's in motion, it's opposed by the magnetic field because it doesn't like having its pressure increased. It also is self-repelling. And ditto for the electric field. But what Maxwell realized that was really important is if you don't have any current, if there is nothing, no wire there, no batteries, no nothing, nothing physical there, all you happen to have is an electric field that's changing in time, you can still have a magnetic field. And we've seen in one of the earlier equations, if you have a magnetic field that's changing in time, you get an electric field. And there ain't nothing physical there. Nothing at all needs to be there for that. So he took that out, making this equation into that, which, as it turned out, looks an awful lot like Maxwell's third equation. Here's Maxwell's third equation, and here's Maxwell's fourth equation. This one for electric field is a function of a moving magnetic field, and the magnetic field is a function of an electric field in motion. And they're almost identical, except that for some reason, the two pesky constants are all on the magnetic side rather than one being here and the other being there, and I don't know why Maxwell did it that way. But when you take a second partial derivative of these, you find that you get something like this, where the rate of change in the rate of change of the electric field causes a displacement in space of the electric field. And the same thing happens with the magnetic field. It causes a change in space in the magnetic field. There's a couple of problems with how this is expressed because they tend to lead us astray. Again, the human condition comes in and gets us to thinking, oh, okay, well then the electric field must move itself through space. And the magnetic field must move itself through space. It must have to do with this, how much space permits or one or is permeable to the other characteristics of space. It has nothing to do with that because an electric field that moves in time does not create directly that what it creates is a magnetic field. And the magnetic field that moves in time is what creates the next electric field. So here's a kind of crude, rough idea of what's going on. You disturb an electric field, and as it is dissipating itself, because it doesn't like itself, it's going to curl a magnetic field. And once it's done, this is time. These take a little, and this is displacement and distance. So the magnetic field, when its expansion curls the electric field, doesn't do it inside of itself, it does it alongside of itself. And you've seen this, the fields aren't overlapped on each other, they're slightly beside each other. When this is done expanding, which takes time, this has been compressed and looks around and says, there's nothing holding me into this tight thing, so I'm going to expand. And it then creates and curls an electric field. And when it's done and there's nothing to hold the electric field in, it expands and curls another magnetic field. So you're going from an electric to a magnetic to an electric to a magnetic to an electric. And each one of these, when this one is gone, the only thing out there in space is what it created, which is its medium of propagation. And when it is gone, the field it created it has finished its job as a medium of propagation. And as it dissipates, it creates that. And so what they're really doing is they're taking turns acting as the pressurized domain of air and the ambient side of air. And they just keep passing it back and forth. And because there's nothing physical being moved, there's no friction, and so it can continue to go on forever until it runs into something. And what Maxwell found, of course, is that when he took those equations back here and further solved them, he got this, which looks just like what we did with air. Now, I got to find where I wanted to pick up from here, because now we're ready to do a direct comparison between the two. And that's down. We've been through this, so I'm going back down now to where we'll pick it up. Come on. Here. When we got done looking at the speed of sound, we decided that this is equal to the product of two velocities, how quickly the pressure will expand if it's unopposed, and how much the others would expand if it was unopposed, but the two are working in opposition. And since that is equal to those, we know that this is equal to that, is equal to that, and if we take the reciprocals, we have that, and if we pull the one out, we have that. And those are reciprocals of two speeds that operate, forces that operate in opposition to each other. Well, this is what Maxwell started out with, and Coulomb started out with, but we realized that what's happening with the two fields is exactly the same results of self-repulsion as happens with air between the pressurized and unpressurized part. But because of the way they did their experiments, all they were finding was the reciprocal. And because they thought it went through empty space, it must have to do with something in empty space, like its permittivity and its permeability. But this is the equation they got. So it turns out, once you take them apart and look inside to see what is physically going on between the pressurized and unpressurized air, or between the field being forced to curl and not wanting to, and the other being allowed to uncurl because it's the stronger of the two, the same forces are going on between the two mediums. It's just that the mediums of light and the light are the same thing. Wrong direction again. So, what we've got is that waves and matter and waves and energy waves are both waves, but they're totally different kinds of waves. A wave that's nothing more than a disturbance in matter requires matter to disturb. A sound wave is nothing more than a disturbance in ambient air that pressurizes something. But It doesn't like that, and the pressure tries to move, and the medium's behavior in passing that along propagates sound. If you have to have matter to disturb, well, it's got to be there. Be whether the sound wave is there or not, it's got to be there waiting for it. It's got to be everywhere the sound can go. And so you have to have all 5 of those requirements for a medium of propagation. But an energy wave propagates itself, and if there's 2 working together, then they have to, and one can only curl the other by uncurling, can uncurl by uncurling the other, and the 2 are operating in opposition, then you have the same thing going on, but it's going on directly between the 2 energy fields themselves. And there's no friction involved because there's no matter involved, so it goes on all the way across the universe as long as it doesn't get disturbed. And so you don't need the 4 of the 5 requirements for that kind of a wave. And the problem with Maxwell, with Mitchelson and Morley, when they proved there was no medium of propagation, was they're looking for a physical thing that permeated all of space through which the light could propagate and would be stable and the light would move through it. They were looking in the wrong place for the wrong thing because they had a bunch of implicit assumptions skyhood at work. And they didn't find what they were looking for because the energy in light provides the energy and all of the dynamics of interaction that do the same thing. They were looking in the wrong place for the wrong thing. Oh, I'll go back to this one. There's another message in here. This progresses at the speed of sound. We already know that, okay? It takes, the speed at which the fields interact with each other, and you take the square root of their product, you get the speed of sound. So what it means is that the sound is propagating distance, time, at a fixed speed, okay? Now where does that start? Well, it starts where the electric field got disturbed, pressurized somehow, and began the process of interacting as it tries to relieve its pressure, creating a magnetic wave. And later, when that pressure of the field is run out, the magnetic wave can expand and create the next electric wave. There's a point of origin. The reason for this second look at this thing is there's a place where that starts. Okay, so I have a burst of light. One burst of light. And from that burst of light, if it's a multi-directional like a light bulb, it'll race off in all directions at once at the speed of light. Now, I have a question for you. If I have one burst of light, how many locations can that burst of light take place in the universe? How many locations at which it can take place? One burst of light.
I mean, how many places can it reach?
Hmm?
I mean, how many places can it reach? How many points can it
No, I'm saying how many places can be the point of location?
One.
Okay. So in all the universe, with one burst of light, there can be one point of origin. And the Maxwell's equation tells us that whatever direction it goes off in, it will go on at the speed of light from that location. Are we together there? Then what happens if you're not stationary relative to that location to the measurement you'll get for the speed of light?
Before you go there, if you could tolerate an interruption, I'm a little bothered by, you say it could go any direction.
Oh, I'm talking about a light bulb. I'm talking about a non-direction. If you have a laser, you'll know where it's going. If you have a light bulb, you really don't. The rays are going off in all directions. But they're moving at the speed of light from the light bulb.
Well, what I was going to ask is relevant to the so-called photon model, is that I'm not certain why it goes off in a specific, I mean, you have an event, such as X-rays hitting anode or cathode or whatever. And then, I shouldn't say that, an electron hitting a plate, and then you have a burst of light. I guess the thing that's bothering me is from your diagram there, it looks like it should go off in all directions, like throwing a pebble into the water, rather than one specific direction.
It depends on whether you're looking, it depends on the level of specificity you're looking. Let's take a light bulb. A light bulb is putting out photons in all directions. If you follow any one photon, it has a specific direction. But if you're just looking at the light in general of the bulb and can't distinguish one photon from another, then wherever you are around the light bulb, you'll see pretty much the same thing. Okay, but wherever, and you go to a distance from the light bulb, and whatever you read will have come at you at that speed from that location. So what I'm really saying is that that location and that speed will determine when you will see whatever left there. Are you comfortable with that? That's really all I'm trying to say here.
Yes, if I have any other questions, let me wait till the end of the session.
Yeah, but I want to be sure I answer your question, because it's a good question. And I want you to feel comfortable that what I'm saying here is if you have one location and whichever way the light goes, it goes at that speed, and you capture it and you're in motion relative to that location, are you going to get the same answer? Assuming it travels constantly at that speed, which is how fast the fields can push each other. And what I'm saying is, does this raise any question in your mind about the second postulate? That you will always see light move at the same speed regardless of the source true, but regardless of the motion of the observer, questionable. Unless you have more than one, unless the location, if the observer is going to see it move at the speed of sound, then the location has to move along with the observer. Otherwise, it's going to see a different speed. So the question is this fact that you're in motion, is that going to cause the location of where a burst of light happened to move with you? If not, you have a question about the second postulate of relativity. I'm just raising the point. So, light's propagation is not magical. The electric and magnetic fields just take turns creating each other. Each is the medium at one point and the wave being propagated, and then the other takes over as the medium and the other is the wave being propagated. Each creates the other alongside of itself, and that displacement plus the time it takes them to expand and contract is what decides they move themselves to empty space, and that decides the speed. And the reason it's absolutely constant, which was considered to be sort of magical, is simply because everywhere space is empty, it's the same, it's empty. There's nothing to interfere with the speed at which the two waves can interact with each other, and so that movement can go on forever in empty space, and the speed will never change. You run into a cloud of cosmic dust or Newton's lens or something that interferes with that interaction, you'll get a different result, but not in empty space. So it's just the laws of physics at work. Two mediums that interchange each other, that are directly energy, don't have the problems of having to push matter around, but their speed is determined by the characteristics of the medium of propagation. It's just that the mediums and the wave are the same things, interacting with each other. But now we know, to this logic, and I'm not saying this is absolutely not unprovable, but it's a very logical construct that says that the two fields work exactly like the air does propagating sound.
You've used the expression empty space, and you've also used the expression medium.
Yeah, a medium would be something that actually, you have to be careful using the word physical physical, because energy is energy physical or not, you know. But a medium is something that carries away, causes it to move. That some of them are physical, air, steel, water will cause sound to move. Light, the medium is the energy fields themselves that interact with each other. Okay? When the electric field creates the magnetic field, and then the electric field is gone, and the magnetic field creates the next electric field, and then the magnetic field is gone, and the electric field creates the magnetic field. You can see that this, as this is created, it becomes the medium of propagation for that, because when it's gone, it creates the next one.
I'm not following. Either there's a medium there or not, it seems to me. Now,
Okay, but we're arguing semantics at that point. You know, I feel a little bit like Clinton. You know, we're arguing what is a medium. If a medium is that which causes a wave to move forward, and the magnetic field is the thing that absorbs the electric field and causes the next electric field to appear in a different place, therefore move forward, then I'm saying its action is that of the medium. It's doing the same thing that air pressure, that air molecules are doing in moving back and forth with each other. It's just that the energy fields are doing it directly.
but if you have put some convincing stuff up to show the equations relating to sound and the equations relating to light are similar, if not the same. Now, in regard to sound, you've got a medium. The medium is the molecules of air
Right.
that exist between you and
Right.
me, and they hit each other until the one that's close to your ear hits your eardrum. That seems pretty clear. Could you reason from the similarity of the equations relating to sound and light that for light there is a medium of the same nature as that of sound?
No, there is not.
Well, you say there is not.
No.
But
Yeah.
can you reason that from the similarity?
No, what I can reason from Maxwell's equations and the interactions it involves is that you do not need a medium like sound has, because the waves move each other directly. They don't have to disturb some physical medium to move themselves through space, because they take turns creating each other. So what I'm really saying is you don't need one. You might want to say there is one, but you don't need one. It's a superfluous concept.
The medium is the message.
Yeah, the medium is the message. That's really what I'm saying. I'm not saying you prove there isn't one, I'm just saying you really don't need one. Because you can entirely describe everything that happens without resorting to one.
But can you also describe everything that happens by resorting to a medium? Is that not an alternate?
You could also do it by resorting to a medium. Yes, you could, but nobody's been able to do so. And that's why Einstein created the theory of relativity. But Einstein made some assumptions doing that creation, and that is there's no explanation for why the speed of sound would require a unique reference frame. Remember that? The whole reason Einstein created relativity was because Maxwell had come up with some equations that said the speed of light will always be that, but you got to measure it from a particular, some magical unique reference frame. What I was trying to show in that point of origin and the light going out at its speed is that all that Maxwell was saying is you got to be stationary relative to the point of origin of the light you're observing, or else you aren't going to observe it accurately. Einstein said, oh, he must be magically saying there's one inertial reference frame that's better than all the others. And in fact, there is, and Maxwell told us how to find it, but that's another paper. But Einstein basically said, gosh, there's nothing going to be magical about one inertial reference frame from another, because Galileo and Newton already proved we get the same answer in all of them, right? In fact, that's the subject of my next paper that we'll get to.
I'm sorry. Say something to that. I have a question. I think that what you are saying now is not founded. You must tell exactly where you mean that Maxwell was that opinion and what you tell now. It's not right. The electric and magnetic radiation do not need the field. It's not right. Because
I translate for my hearing aids, I'm having a real hard time.
I think basically what it's boiling down to.
What you are saying that the magnetic electric radiation do not need field. Or maybe it's not right. Maxwell never said it. It's what you are saying.
He's saying that Maxwell did not say that there was,
The problem is that
Maxwell assumed there was a beam.
the problem is that
Maxwell may have assumed that. In fact, I suspect that Maxwell did assume, because Maxwell did not question. Remember,
familiar with Maxwell equation? Are you familiar? Are you familiar with Maxwell equations?
He just had Maxwell's equations.
You missed the first, you missed the first part.
Yes.
Can we
You
let
went
him
through
finish?
Maxwell's equations.
Can we let him finish and then we can answer?
It might be, because
But it has to be started with
He's neither trying to prove nor disprove the ether theory. This is an alternative that says that it's possible to explain light's propagation without resorting to an ether theory.
yeah,
It doesn't disprove.
you don't need an ether, but this explanation shows that even if there is not an ether, the sound will have, if there is no ether, what this is saying is that Maxwell was 100% right. Even on the part Einstein threw out, and that is you'll only get the right measurement if you're stationary relative to the point of origin. Einstein made the point of origin relative, not absolute. He said there's nothing absolute. Maxwell said there is something absolute. You won't measure light at its proper speed unless you are stationary with its point of origin. And he gave you additional terms you had to use if you weren't stationary with its point of origin.
I have one sentence to that. What you said is the same as if you want to pull yourself from pool by your head this way, and that you can pull yourself from a pool if you are holding you by the hair.
Mhm.
This is exactly the same theory. You cannot pull yourself from pool by your own hair. It's impossible.
Can we let him finish?
Agree to disagree. Agree to disagree.
Boy, I'm taking way too much time here. So anyway, what this does show is that if you follow Maxwell's equations and go in to look at where epsilon and mu come from, you find out you don't really need an ether in order to have light propagate itself through space indefinitely at a constant speed. But you do have to recognize that Maxwell was right when he said, if you aren't stationary with the source, you need additional terms, and that is what Einstein rejected when he adopted the relativity principle as his first postulate. And so I'm saying there's a real reason to question that first postulate. Now, does anybody want to have me go through the other speech?